Have you ever looked at a big welded structure, maybe a bridge, or even just, something fabricated in a workshop and thought about the challenges? Or maybe you've seen the other side, something welded perfectly straight, looked great, and then later it's twisted or warped or even cracked.
Oh yeah, that's a classic problem. Really frustrating for engineers.
It seems to defy logic, right? Why does that happen?
Yeah.
What are these invisible forces that can just take over and change the shape of solid metal?
It's a fascinating area.
So our mission today, in this deep dive, is to sort of unpack that mystery. We're diving into the world of residual stresses and distortion in welded materials.
Yep. Two sides of the same coin, really.
We'll look at sources explaining what they are, what causes them, the different ways they show up, and the really critical factors that, make them better or worse.
Get ready to understand why heat and metal sometimes don't play nicely together.
So where does it all start?
Well, fundamentally, it all boils down to physics. It's about how materials behave when you heat them up and cool them down unevenly, which is exactly what welding does.
Right. Localized heating.
Precisely. And it's not just about aesthetics, like things looking bent. It's deeply tied to structural integrity. Whether it's a huge storage tank or, a ship hull, understanding this is absolutely critical for safety and performance.
Okay, let's really get into that. The genesis of these invisible forces. Welding means intense, local heat. How does that leave behind these locked-in stresses? It feels like heat should just dissipate.
It does, but it leaves something behind. It's basically a two-phase process. Think about phase one, the heating.
Okay.
You form that molten weld pool. It's incredibly hot, and metal expands when it's hot, right?
Basic physics.
But it's surrounded by all this cold or much cooler parent metal. That colder metal doesn't want to move. It resists the expansion of the hot zone.
Ah, okay. So it's like pushing outwards but being held back.
Exactly. And that resistance creates compressive stresses in the cold metal right next to the weld. It's being squeezed.
Okay, that makes sense for the heating part. But where did the residual stresses come from, the ones left behind?
That's phase two, the cooling. And this is where it gets really interesting. As the weld metal itself and the metal right next to it that got hot, the heat-affected zone, or HAZ, as they cool down, they want to contract, shrink.
Naturally. Things shrink when they cool.
They want to shrink quite a lot, actually. But again, the bulk of the surrounding parent metal, which didn't get that hot, is still there. It didn't expand much, and now it resists that contraction.
So the weld tries to pull inwards, but the rest of the structure says nope.
Pretty much. And that resistance, that internal tug of war, is what creates powerful tensile stresses. The weld and the HAZ are literally left in a stretched state, pulled tight by the surrounding colder material.
Ah, so residual means they're just left over, like a footprint of the heat cycle.
Exactly. It's a permanent stress state locked into the material after everything is cooled down. These stresses can even cause the material to permanently deform or yield during cooling until they drop back to the yield stress level. Even then, an elastic strain stays locked in.
So the weld is essentially pre-stretched elastically.
Yeah.
Okay. But are these stresses just random, or do they form patterns? Are they predictable?
Oh, they form very predictable patterns, and understanding them is key. And the forces are huge. Consider the volume change alone.
Volume change.
Yeah, think about steel. When the molten weld metal solidifies, its volume shrinks by about 3%. Then, as that solid metal cools down to room temperature, it shrinks another 7% or so.
Wow, that's nearly 10% total shrinkage it wants to do.
Roughly, yeah. Imagine trying to force something to shrink by 1/10 of its size within a structure that won't let it. That's the kind of internal stress we're talking about. It's significant.
Okay, so how does that stress distribute itself?
We mainly talk about two directions.
Yeah.
First, transverse stresses. These run perpendicular or across the weld line. Interestingly, their magnitude is often relatively small, but don't let that fool you. They can cause really substantial distortion.
How can small stresses cause big distortion?
Think about pulling the center of a long, thin strip tight while pushing the ends in. A little force can cause a big buckle or bend. The pattern is usually tension in the middle section, maybe low magnitude, and then compression at the ends of the weld.
And does the length of the weld matter?
Hugely. Crucially, the longer the weld, the higher that tensile residual stress in the middle tends to become, often reaching the material's yield stress limit.
Okay, so longer welds, potentially more transverse stress issues. What about along the weld?
Those are the longitudinal stresses. They run parallel to the weld. And here, the situation is often more severe in terms of stress magnitude.
How so?
The weld metal itself and a band of the parent plate right next to it are often left at or very near the material's yield stress and tension.
So right at the limit of where it starts to permanently deform.
Exactly. It's stretched to its elastic limit. As you move further away from the weld into the colder plate, those tensile stresses drop, pass through zero, and then become compressive to balance things out.
Right, the forces have to balance overall.
They do. And another key point. Higher heat input during welding, like using a slower travel speed or higher current, tends to create a wider band of this high tensile residual stress along the weld.
Which sounds like it could make things worse.
It can, especially for things like fatigue life in structures that see repeated loading, like bridges or cranes. That wider band under high tension is more susceptible.
Okay, so this sounds pretty much unavoidable in most welding. Is it always a problem? Or are there cases where, we can live with it?
That's a really important practical question. And no, it's not always detrimental.
Oh, like what?
Think about many common structures, standard storage tanks, most building frames, low-pressure pipework, even things like metal furniture or domestic equipment. Often, the residual stresses in the as-welded condition have very little impact on how they perform in service.
So the design just accounts for it, or the loads are low enough?
Pretty much. The inherent strength and the safety factors used in the design mean those stresses aren't the limiting factor.
But when do they become a big deal?
Oh, there are definitely times when they are critical, even dangerous. The most obvious one is distortion.
Right, the visible warping.
Exactly. If your welded component is supposed to be flat or straight and it ends up bent or twisted, it's often simply not fit for purpose. It won't assemble correctly or it won't function as designed.
Makes sense.
What else? Dimensional stability, especially during machining. This catches a lot of people out.
How so?
Imagine you weld something, it looks okay, maybe a little distorted but acceptable. Then you need to machine it to very precise dimensions. As you start removing metal, especially near the weld.
You're changing the stress balance.
Precisely. You remove material that was holding some of that residual stress, and the whole thing can suddenly warp or spring out of shape. Holding tight tolerances becomes incredibly difficult.
So that's why sometimes parts are heat treated after welding, but before final machining.
Exactly. Post-weld heat treatment, or stress relieving, aims to relax those internal stresses so the part stays stable during machining.
Okay, what about more serious failure modes?
Well, residual stresses can significantly increase the risk of brittle fracture.
Brittle fracture. That sounds bad.
It is. It's a sudden catastrophic failure with little warning. In certain conditions, like low temperatures, the tensile residual stresses add to any applied stresses from the load. If the combined stress reaches a critical level at a small flaw or notch, bang.
Is that common?
It was a major issue historically, like with the Liberty ships in WWII failing in cold seas. It forced a huge leap in understanding fracture mechanics and material selection. Today, designs in sensitive applications account for it, often requiring materials with high toughness, especially at low temperatures, and sometimes mandatory stress relief.
Wow. Okay, any other major ones?
Yes, stress corrosion cracking, or SCC. Some metals in specific corrosive environments, think certain chemicals, or even salt water for some alloys, will crack rapidly if they are under tensile stress.
And the residual stress provides that necessary tension.
Exactly. It can make a material susceptible to corrosion cracking even when there's no external load applied. Stress relieving can significantly slow down or prevent SCC in many cases.
So for a designer, this is huge. They need to know if stress relief is needed, maybe by code or insurance, especially for things like pressure vessels.
Absolutely. They have to consider residual stresses when choosing materials, setting allowable working stresses, and especially when dealing with fatigue, those fluctuating loads on bridges or cranes we mentioned. The residual stress state directly impacts fatigue life.
Okay, that gives us a good picture of the stresses. Now let's talk about the visible result, distortion. What's the fundamental link? Why does the stress make the metal move?
It's a direct consequence. Remember how the heating and cooling are localized and non-uniform?
Yep. Uneven expansion and contraction.
Right. This creates those internal stresses. Now, if those stresses generated by the thermal expansion and contraction trying to happen actually exceed the yield strength of the parent metal, particularly when it's hot and weaker.
The metal gives way.
Exactly. It undergoes localized plastic deformation. It stretches or compresses permanently just a little bit in specific areas. It can no longer just spring back elastically.
And that permanent local bending or stretching is what we see as distortion.
That's it. That permanent set, that localized yielding, means the overall dimensions of the component change, usually shrinking overall, and the structure visibly distorts. It's the point of no return, dimensionally speaking.
Okay, that connection is clear now. Stress builds up, hits the yield point locally, causes permanent deformation, which we see as warping or bending. So what are the common ways this distortion actually shows up? What shapes does it take?
There are several classic types. The most basic are longitudinal shrinkage and transverse shrinkage.
Just overall shrinking along and across the weld.
Pretty much, yeah. The weld area physically gets smaller as it cools and contracts, pulling the attached plates with it.
Okay, what else?
Angular distortion. This is really common, especially in fillet welds and single-sided butt welds. It happens because the contraction isn't uniform through the thickness of the plate.
How does that work?
Think of a simple single V butt weld. You lay down the first weld run at the root. As that cools and contracts, it pulls the top edges of the plate closer together than the bottom, causing the plates to rotate upwards, creating an angle.
Like closing a hinge slightly?
Exactly. But you can often counteract this. If you use a double-sided V-butt joint and alternate weld passes on each side, you can balance the contraction forces and keep the plates flat.
Clever. What about fillet welds? Like a T-joint?
Same principle. A single-sided fillet weld joining a vertical plate to a base plate will almost always cause angular distortion, pulling the vertical plate out of square.
So you end up with not quite a 90-degree angle.
Right. Again, using double-sided fillet welds, ideally welded simultaneously, can help prevent that specific angular distortion of the upright leg. Although be careful, even double-sided fillets can sometimes cause the base plate itself to distort angularly.
Like whack-a-mole. Okay, what other shapes?
We see bowing and dishing. Longitudinal bowing happens when the weld line isn't on the neutral axis of the section you're welding.
Neutral axis, like the center line of its stiffness.
Sort of, yeah. If the weld is off-center, the longitudinal shrinkage along the weld causes the whole member to bend into a curve, like a bow.
Okay. And dishing?
Dishing is like bowing but in two directions, creating a shallow dish shape. You often see this in, say, clad plates, where one layer might shrink more than the other, or very commonly in large, thin panels with stiffeners welded on. The angular distortion at each stiffener weld adds up across the panel, causing it to dish between the stiffeners.
Right, I can picture that, like a quilt effect almost.
A bit, yeah. And related to that, especially in thin plates, you get buckling. This is caused by those long-range compressive stresses we talked about earlier. If the plate is thin enough, those compressive forces can make it pop out of plane, causing waviness, rippling, or larger dishing or bowing.
So thin materials are particularly tricky.
Very much so. They have less inherent stiffness to resist those buckling forces. And one more detail, the size of the weld matters directly. Increasing the leg length of a fillet weld, for instance, means more weld metal.
More shrinkage.
Exactly. More shrinkage, more stress, and generally more distortion. Keeping welds appropriately sized, not excessively large, is crucial.
Okay, so we know what distortion is and why it happens, those residual stresses exceeding yield strength. Now, the big question, what factors influence how much distortion occurs? And maybe what type we get? It seems like a lot of things could affect it.
Absolutely. There are several key levers we can pull, or at least need to be aware of. The core idea, remember, is that uniform heating and cooling would cause almost no distortion. It's the localized heating and the restraint from the surrounding structure that generate stresses high enough to exceed yield.
Got it. So what are the main factors?
First and foremost, parent material properties. This is huge.
Okay, like what properties?
The big one is the coefficient of thermal expansion. How much the material expands and contracts for a given temperature change.
Higher expansion means more potential trouble.
Definitely. Higher expansion means greater potential movement, which leads to higher stresses when restrained and ultimately more distortion.
Is there a common example of this?
Oh, absolutely. Stainless steel versus plain carbon steel. Stainless steel generally has a significantly higher coefficient of thermal expansion A&D, lower thermal conductivity than carbon steel.
Lower conductivity, meaning the heat stays concentrated?
Right, it doesn't spread out as quickly. So combine higher expansion with more localized heating, and stainless steels tend to distort much more dramatically during welding than carbon steels. You have to approach them very differently.
That's a really important practical point. So knowing your material's thermal properties is step one. Anything else?
Thermal conductivity itself matters. Higher conductivity generally helps dissipate heat faster, which can mean lower peak temperatures and potentially lower residual stress. Yield strength and Young's modulus also play a role in how the material responds to the stress.
Okay, material properties. What's next?
The amount of restraint, how rigidly the parts being welded are held in place.
Right, you mentioned clamps or strongbacks earlier. Does more restraint mean less distortion?
Yes, generally, if you physically prevent the parts from moving while welding and cooling, you can significantly reduce the final distortion.
Sounds like a good thing.
It can be, but there's a critical trade-off. While restraint reduces visible distortion, it forces the material to accommodate the shrinkage internally. This results in higher levels of residual stress locked into the component.
Ah, so you trade less bending for more hidden stress.
Exactly. And that higher residual stress significantly increases the risk of cracking, especially in the weld metal or the HAZ, if the material is even slightly susceptible to cracking.
So too much restraint can be counterproductive, even dangerous.
It can be. You have to balance the need to control shape with the risk of high stress and cracking. It's not always simple.
Okay, what else influences distortion?
Joint design. The actual geometry of the weld joint makes a big difference.
We touched on this with single versus double V welds.
Right. For butt joints, choosing designs that inherently balance the thermal stresses through the thickness helps minimize angular distortion. Double-sided joints are often preferred over single-sided for this reason, where practical.
And for fillets.
Again, double-sided fillets are better than single-sided for controlling angular distortion of the upright part, especially if you can weld them at the same time to balance the forces. The joint design dictates how the heat flows and contracts.
Makes sense. What's number 4?
Part fit-up. How well the pieces align before welding.
Seems basic, but important.
Crucial for predictability. You want the fit-up, especially the gap between parts, to be uniform along the joint. This helps ensure shrinkage is consistent.
And what happens if the gap is too big?
This is a really common issue. An excessive joint gap means you have to deposit much more weld metal to fill it.
More weld metal equals more shrinkage.
Bingo. More weld metal means more heat input, more material contracting upon cooling, and almost always significantly more distortion. Controlling the gap is critical. Also, you need adequate tack welding beforehand.
To hold things in place.
Yes, to prevent the parts from moving relative to each other during the welding process itself, which can also lead to unpredictable distortion.
Okay, fit up is key. What's the last main factor?
Finally, the welding procedure itself. This covers things like the welding process used, famously TIG, MIG, stick, the parameters, current, voltage, travel speed, and importantly, the sequence.
How does procedure affect distortion?
Mainly through its effect on heat input and weld volume. A fundamental rule is to keep the weld volume to the minimum required for structural integrity. Smaller welds generally mean less distortion.
Use the smallest weld that does the job.
Exactly. And the welding sequence, the order in which you make multiple welds on a component, is critical for balancing thermal stresses. Experienced welders use specific sequences, like backstepping or welding towards the point of maximum freedom, to counteract distortion as they go.
So carefully planning the path and order of welding.
Yes. The aim is to try and balance the thermally induced stresses around the component's neutral axis as you build up the weld. It's about managing the heat and contraction systematically.
Wow, okay. So pulling this all together, what's the big picture? It seems welding is far more complex than just melting metal together.
Oh, absolutely.
It's this incredibly delicate dance of intense heating, rapid cooling, expansion, contraction, all leaving behind these powerful, invisible residual stresses. And understanding those stresses and the different ways they cause parts to distort, bowing, buckling, twisting, it's just fundamentally critical, isn't it?
It really is. And by recognizing how all these factors we discussed interact, the material properties, the level of restraint, the joint design, how carefully you fit things up, and the specifics of the welding procedure, you actually gain a huge amount of control.
So it's not just luck.
Definitely not luck. Managing distortion and residual stress is a core engineering challenge. It requires informed decisions at every stage because every choice impacts the final shape, the internal stress state, and ultimately the integrity and performance of the welded structure.
Well, that certainly gives us a much clearer picture. That wraps up our deep dive into the fascinating world of residual stresses and distortion in welding. Hopefully you listening have a better handle on these fundamental challenges now.
And thinking about all this complexity raises a final thought for you. We know eliminating welding often isn't practical, and completely preventing distortion is incredibly difficult with current methods. So, how might things change in a future where materials could perhaps self-heal damage or even self-correct for these kinds of stresses at a microscopic level? How would that fundamentally alter the way we design and fabricate complex structures?